Theoretical physics rests on a category error. Since 1908, the discipline has operated under the assumption that dimension is synonymous with a vector direction in a manifold, treating time as a geometric coordinate on the exact same footing as space. This is the Minkowski metric. It unifies space and time by assigning time the coordinate index of x0, isolated from the spatial terms by a negative sign. The tensor calculus that followed this formulation only required indices and a signature. It no longer asked what kind of physical dimension x0 represents. At the phenomenological level, the identification fails. Spatial displacements commute. Moving east, then north, puts you in the same location as moving north, then east. Temporal experiences do not. There is no operational sense in which experiencing Tuesday, then Monday is equivalent to Monday, then Tuesday. The vectorial treatment of time erases this asymmetry by design. When modern models encounter anomalies, the default reflex is to add more indices. Theories like Kaluza-Klein or recent 1+ 3-dimensional models propose multiple temporal axes, redistributing coordinates between space and time while keeping the vectorial conception of dimension untouched. Treating time as a vectorial direction is an algebraic convenience. When applied to physical reality, conflating a mathematical index with a dimensional container creates topological contradictions that are usually mistaken for features of the world. The dimensional reading of time was never forced by empirical data. The founding mathematics of relativity were built on operational synchronization protocols, not on claims about the physical geometry of a 4-dimensional world. In 1895, Hendrik Lorentz introduced local time as a strictly auxiliary device. It was a bookkeeping parameter but allowed moving electromagnetic oscillators to be described as if they were at rest. Lorentz achieved his results without attributing any dimensional ontology to the variable. Henri Poincaré finalized the group structure and the invariant quadratic form while explicitly refusing to promote the time label to a world axis. He maintained that the simultaneity of distant events was defined by a synchronization convention, not a property of a manifold. The Minkowski trap was set in 1908. Hermann Minkowski, drawing on the Göttingen theory of quadratic forms, read the transformations as the invariance group of a geometric manifold. He declared that space and time by themselves were doomed to fade into shadows, replaced by a 4-dimensional union where time functioned as a coordinate. This interpretation was canonized by the 1913 Teubner anthology. The collection fixed the genealogy of Lorentz, Einstein, Minkowski while excluding Poincaré, one author who combined the theory's full invariant structure with a non-dimensional reading of time. The concept of space-time is a historically contingent mathematical artifact. It was an interpretive decision that eventually became an invisible assumption in theoretical physics. General relativity contains its own internal rejection of fundamental time. This is exposed by the theory's own constraint formulations, specifically the Beierlein-Sharp-Wheeler, or BSW, action. This equation recasts general relativity in a form built entirely from the 3-dimensional metric and its derivatives. It eliminates explicit temporal variables. The entire action is evaluated along a parameter S, which can be relabeled arbitrarily without changing the physics. In this formulation, S labels a sequence of 3 geometries that satisfy a constraint algebra. It measures how a 3-dimensional manifold deforms relative to a static background. It does not measure the progress of an independent temporal dimension. The ADM formalism confirms this by showing that the lapse function and shift vector, the components that describe how time passes, are pure gauge constraints. In canonical gravity, time is a derivative artifact of foliation choices. Because the mathematics of gravity already reduce time to a constraint label, we can move past the temporal dimension entirely and define the structure that generates the shadow. The timeless counterspace and shadow gravity framework, or TCGS, begins with axiom A1. It posits reality as a smooth, static 4-dimensional manifold. This is counterspace. It is a dense, static block of strictly geometric and informational content, endowed with a bulk metric and a global content field. Counterspace contains the full content of all admissible configurations simultaneously. There are no shifting states. Past and future are coordinates within this static whole, not regions of a flowing temporal axis. The observable universe is a 3-dimensional shadow manifold embedded within this static informational bulk. We do not perceive the counterspace directly. We perceive the projections it generates. Substituting a temporal dimension with an informational counterspace provides the necessary container for the universe's full complexity while adhering to the timeless requirements of gravitational constraint physics. The interaction between the shadow world and the static bulk is defined by mapping. We represent the observable universe as a three-manifold, sigma, interacting with the counterspace C. The immersion map, X, defines physical observables on the shadow world as direct pullbacks from the bulk. The properties we measure are determined by where our slice intersects the geometric content of the counterspace. To compare different states, we use a foliation parameter, lambda. This is a gauge label that tracks a family of these embeddings as they sample the block. Shifting the foliation parameter updates the physical properties registered on the shadow. As the plane moves through the block, the intersections change, causing the mapped geometry on the surface to morph. The shadow appears to change because it samples varying informational density within the counterspace. The evolution we measure is the result of moving through a static territory. Time evolution is a cartographic artifact. It is the geometric consequence of comparing adjacent slices of a static reality. The same mapping logic explains why physical laws appear to break down at extreme scales. Axiom A2 defines the singular set, S, a collection of conserved, highly concentrated informational geometries inside the bulk. These structures distribute through the counterspace to provide the universe's foundational architecture. They act as the anchors for the structures we observe in the shadow. Extreme phenomena like black holes are geometric traces of this singular set. When our shadow slice intersects a node, the resulting distortion appears as a gravitational well where standard coordinates become unusable. At these limits, the mapping process loses coherence. The framework calls this the unfoliator state, a regime where the geometric conditions required for a stable foliation are no longer met. The notion of a global clock collapses at singularities because the projection map itself has dissolved. The breakdown of time in these regions is a natural limit of the mapping geometry. A timeless ontology provides a direct solution to macroscopic gravitational anomalies, specifically the anomalous rotation curves observed in galaxies. The standard lambda CDM model assumes galaxies are surrounded by invisible dark matter halos to account for their rotation speeds. The TCGS model views these kinematics as a consequence of the geometric projection from the bulk. Axiom A4 requires parsimony, forbidding the invention of unobserved dark species. Instead, it posits an extrinsic constitutive law that determines how the shadow responds to the embedding geometry. In this regime, galactic kinematics match the weak field shadow of the embedding's response. The outer rim accelerates to match the internal speeds without adding mass, aligning with observations from modified dynamics. Dark matter is a misdiagnosed projection artifact, the error that occurs when a three-dimensional shadow is mistaken for the true container of reality. This projection logic also applies to the biological sector. If the counterspace contains the informational content of the world, then that content includes organizational structures. Counterspace encodes organizational content alongside physical geometry. In the biological sector, this content manifests as the set of viable genetic and morphological configurations. What we perceive as chance mutation or deep time are artifacts of our shadow world sampling these pre-existing informational patterns. This explains convergent evolution. Lineages as different as mollusks and vertebrates converge on identical structures, like camera eyes, because they are sampling the same slice-invariant corridors in the biological bulk. The structure exists as a geometric stability in the counterspace before any lineage reaches it. The world possesses a fourth dimension, but its role is informational rather than temporal. It provides the richness and organizational density that a three-dimensional representation lacks. Time is the cartographic gauge of our passage through a structured informational territory. It is the label given to progress through a static reality.